Today we're going to talk about digital and analog and what do these two terms mean. Basically, they're both methods of measuring quantity, and two examples that we have here are time and temperature. So we have an analog version of measuring time, which is this timepiece here, and a digital version. And we have an analog version of measuring temperature, which is a glass thermometer, and a digital version of measuring temperature. Now let's for a second just consider Morse code as a coding method. Morse code uses dots and dashes. It's a two-symbol method to represent 26 characters of the alphabet. So A is a dot on a dash, and B is a dash and 3 dots. But there's only two possible symbols that can be used, either a dot or a dash. This is similar in computers, which use binary code, and digital depends on binary code. Binary code substitutes dots and dashes with a different two-symbol method, which is using ones and zeros. Each one of these is known as a binary digit or a bit. So this 1 here would be a bit, and this 0 here would be a bit. The process of converting analog data into digital data is known as encoding, and the process of converting digital data back into analog data is known as decoding. So what does analog and digital mean? Let's consider an everyday example of analog usage. In homes, we may have two different lighting methods, a dimming switch or a standard light switch. As you can see here, we've got a dimming switch. The dimming switch can alter lighting from 0% up to 100% light. This is considered as analog as the range of quantity is continuous and can take a value anywhere between the range of 0 to 100. Now let's consider the alternative. The alternative to a dimming switch is a standard light switch. The light switch only has two possible states. It's either off at 0% light or it's on at 100% light. This can be considered as digital. The state is either on, in binary that would be considered as a 1, or off, which in binary would be considered as a 0. So if we look at these two again, you can see here we have our dimming switch, which would be considered as analog, because it can go from 0 to 100 and take anywhere within this given range. If we consider the alternative, we have a standard light switch which is either on or it's off, which can be considered in digital as a 1 or a 0. It's only got two possible states. But life is an analog experience and not a digital one. We experience varying levels of light, sound, touch, smell, temperature. So how can we turn these into a digital data that computers understand? Let's consider the thermometer for a minute. An analog thermometer measures temperature. Let's say in our case it's a continuous quantity anywhere between 0 degrees at the bottom here up to 100 degrees at the top here. There's an infinite range between these two, because even if we had 1 degree just here, we can still break this down below into 0.5, and we could go lower than that, infinity, so we could always add another one. So there's an infinite range in between 0 degrees and 100 degrees that this could possibly take. A digital thermometer, however, uses a quantity from the binary system of only two possible values, which is 1 or 0. So how can we represent the temperature between 0 and 100 degrees using only ones and zeros? Let's consider representing the thermometer using one bit of digital data that would divide the quantity into two possible zones. So if we split it into two zones, we could say from 0 to 50 degrees is a 1, and from 50 degrees up to 100 degrees would be a 0. But that wouldn't be very accurate, because the chances are, if we want to know the temperature of something, we don't want to have such a massive range of 50 degrees. So what we can do is break this down even further, using two binary digits and dividing it into 4 possible zones. So here's our 4 zones. So we could say a 1 and a 1 is anywhere between 25, and a 1 and a 0 is 25 to 50, a 0 and a 1 is anywhere between 50 and 75, and a 0 and a 0 is anywhere between 75 and 100. But again, that's not particularly accurate. Adding another bit allows 4 zones of temperature, and if we have 3 bits in total, this allows 8 zones. So if we continue to divide this up even further, we could have 8 possible zones. We can keep going with this, and if we get up to 8 bits, such as so this in total is 8 bits, and 8 bits is known as a byte. 8 bits will divide this into 256 possible zones. The more bits or bytes of data, the more accurate the thermometer can be made. This, however, still loses data, and it's not as accurate as this analog version here. Digital will never ever be as accurate as analog. So if we consider this again, using an example of replicating sunlight levels using a digital light sensor. So let's say our light sensor measures light from the sun. And here's our sensor. The light from the sun is a continuous quantity anywhere between 0% light, which is darkness, and 100% light, which is white. And remember, this is an infinite range of values, because you can always break down further and further and further to the decimal point between these two. So it's an infinite range of between 0 and 100% of the light that could be coming from the sun to the sensor. In order for the sensor to replicate the light using a light bulb, the digital sensor must use the binary system of only possible values of 1 or 0. So how can it represent the light between 100% and 0% light? Let's consider representing the light using 1 bit of the digital data that would divide the quantity into 2 possible zones between 100 and 0%. So we could have 100% light and 0% light, So if we divide this into two possible zones, we could have 1 up here and 0 down here. So 1 would represent anywhere between 50% and 0 would represent anywhere between 0 and 50%. Adding another bit would allow us to divide this into 4 possible zones. Adding another bit to make 3 bits allows us to divide this into 8 possible zones. We can continue this again, and if we got up to 8 bits, which would be a byte, we would have 256 possible zones. The more bits and bytes of data, the more accurate the light replication can be. Again, this still loses data, and it's not as accurate as analog, because digital will never be as accurate as analog. So if digital isn't as accurate as analog, then why do we use it? What do we gain from using digital if it's less accurate? Using digital data means data can be copied multiple times without introducing any error. It means it maintains its accuracy. So let's consider an analog wave. So we can take a quantity anywhere along this continuous wave for analog. But if we were going to make a copy of this wave, and I'm going to try and make a copy of this. You can see that error has been introduced. Then if I make a copy of the copy, you can see that more error has been introduced. As an example, let's have a look at an analog machine. So the photocopier is an analog machine. It measures the reflection of light and makes a reproduction of that. If I photocopy a photocopy, then this introduces error. So here's our original. If I photocopy this original, then I introduce some error. The copy isn't quite as good as the original. Then if I make a copy of the copy, then this is even worse than the original copy. And if I copy this copy, then again I keep on introducing more error every time until I end up with what is virtually a blank piece of paper. If I take a Word document which is made up of ones and zeros, and I make a copy of that, then that's exactly the same. No error has been introduced. And if I make a copy of that, then it's still the same. No error has been introduced. I can keep on doing this, making copies of the same Word document billions of times, and all I will get are the same ones and zeros. It's an exact copy of the original here. No error has been introduced, unlike our analog version of the photocopier. Consider this video. How many reproductions have taken place from the recording of this video to transmitting it over the internet to playing it on your device, and it still maintains its quality? If it was an analog signal, then by the time you saw it, the image would be blurred and almost unrecognizable. What are the other benefits of digital? Well, a big benefit of digital is that it leads to storage benefits. Consider the analog example of data storage, which would have been paper sheets, which were stored in folders, stored in filing cabinets, and these are stored in filing warehouses. Now consider the millions of pieces of data that can be stored in a digital database, which can be stored on something as small as a USB. Digital also leads to timeliness. Consider the amount of time spent searching a manual filing store for data. Digital processors can perform millions of operations in a second and can locate information in a database almost instantly, a lot quicker than you'd be able to find it by hand using an analog database system. Consider analog video cassettes and tapes. If I wanted to locate a specific part of a film or an audio track, it would be time-consuming, fast-forwarding, rewinding, playing, looking for the exact area where that was using the analog system. But now consider a DVD and your other digital media, such as MP3s. I can jump to any section almost instantly. Digital leads to increased accessibility as well. The same binary coding can be used for many different types of media, whether it's text, number, video, images, audio. They all use the same binary ones and zeros system. It can also be understood by various digital devices such as phones, tablets, laptops, PCs, Macs, the list goes on. The media can also be combined on just one device. Compare this to an old analog 35mm projector such as this one here. This can only process a film and is unable to do text and number and audio, unlike these various digital devices which can cope with all those different types of media. Hopefully this video has helped you understand the difference between digital and analog. So both are ways of measuring quantity. Digital is discrete, which means it's either made up of 1 or 0, whereas analog is continuous and can take a value anywhere between a range.